Okay, today we will solve this numerical which is actually displayed on the board. Draw SFD and BMD for a simply supported beam shown. Basically, this is a double overhang simply supported beam where the beam has stretched beyond the supports. So this is a double overhang, and this is the way the numerical is given in the in the examination. So this is a simply supported beam where you have got a roller support on one side and an in support on the other side. So the first thing that you have to do is you have to convert this into a free body diagram. A free body diagram is represented by just forces. So instead of this physical support, you need to just write an arrow mark like this, which actually shows that there is a reaction force coming up here. So first thing that you have to do is replace this with okay. Once you have replaced this, then these are the two supports, First you have to name the salient points. Usually we start with the left side support as A, the right side support as B. Then the other salient points, wherever the load changes, wherever the beam ends, those are the other salient points. So name this as C, D, E. So there is no E, so this is E. So if the first step is over, the next step is, even by mistake you may start writing below this diagram. It is always better that you reserve this place for SFD and BMD. Not even by mistake you start making the calculations here. So what I would actually prefer is try to draw the lines below from the salient point so that you can reserve this place for SFD BMD. So now first you reserve this. So it is always better that you start this numerical in a fresh page, maybe on the left hand side of the page, and the calculations on the right hand side, so that you don't have to each time turn the sheets and actually make the calculations and write this diagram. It is always better you see that the whole calculation and this SFD BMD is seen in a single stretch. You don't have to turn the pages. So once you have reserved this, you now we'll make the calculations on the right hand side here. Okay, now to find out the reactions at A and B, which are the supports, as usual, let us take moment about A. So usually we would take the last point, which is the support, but don't take about C. Usually you should actually take about a point where the reaction forces are not known to you. So reaction force at A is not known to you. So therefore, if you take at C, then you will have the reaction force at A, reaction force at B, both in the equations. There will be two unknowns. If you got two unknowns in the equation, you can't solve. So therefore, you should actually take at a point where one of this is unknown. Only then you can get the other unknown. Okay, so I am taking about A. So let us now see how do we actually consider the clockwise moments and anti-clockwise moments and add this. Okay. Is this seen? Okay. Let us now take the anti-clockwise moments about A. So the part of the beam on the left hand side creates an anti-clockwise moment which is like this. So let us take it as negative. So it is negative, and the value is, the load intensity is 30 kilonewton meter, and this length on the left hand side is 3 meters. So this UDL could be imagined as a single point load on the left hand side at a distance of half of this length. So what I do is, so the intensity of the UDL is known to me, 30 kilonewton for every meter. It is actually stretched over 3 meters. So this gives the total UDL on the left hand side. The UDL could be imagined to be placed at the center, so which is actually minus 1 point, which is actually 1.5 meters, which is half of 3. And that is actually negative since it is trying to rotate this in the anti-clockwise direction. Let us see the part of the UDL on the right hand side. The part of the UDL on the right hand side will try to rotate this in the clockwise direction. Imagine about this point, all these forces on the right hand side will try to rotate clockwise if it is downwards. If it is upwards, it will try to rotate anti-clockwise. So the clockwise moment on the right hand side, so let me write it as plus. So again the UDL intensity is 30 kilonewton for every meter multiplied by the total length of the UDL on the right hand side. Is this visible up to this side? Is it visible? Up to here? Okay. So this is spread over 5.5 meters, and this UDL could be imagined to be placed at the center of this. So what is half of 5.5? 2.75 meters. So that is plus. And then leaving this, the next force that we see is RB, which is not known to me. Whether this RB will create a clockwise movement or anti-clockwise movement. What do you feel? This will create a clockwise or anti-clockwise movement? Anti-clockwise movement. Since it creates anti-clockwise movement, I will write it as minus RB into, what is the distance from A? What is the distance from A?
11 meters.
It is 11 meters. It is 11 meters. Okay. And again, okay, RB is done. And what about this load at E? Load at E is 100 kilonewton. And is this clockwise or anti-clockwise? It is clockwise. Plus 100 kilonewton into what is the distance from A? 11 plus 4, which is actually 15 meters. So with this, you can actually find out, you can say that the clockwise moments plus the anti-clockwise moments, the summation of this is 0. So here, the summation of this is 0. You have taken anti-clockwise as minus and clockwise as positive. So you can actually take this RB on the left hand side. So please find out. So to find RB, so 30 into 3 is 90. 90 into 1.5 is 135. So this is minus. So here meter cancels away. So what is left is minus 135 kilonewton meter plus, what is this value? 453.75 kilonewton meter minus, so minus RB can be taken to other side. RB into 11 meters can be taken onto the other side. What is this value? 100 kilonewton. So that is 1,500 kilonewton meter. So here you got kilonewton meter, all these are kilonewton meter. So to have consistent unit, this RB has to be kilonewtons only. Okay, so we get the RB value in terms of kilonewtons. So like this, you can see that meter of all this cancels out with this meter, and therefore what is on the left hand side, all this are kilonewton, the RB value has to be kilonewton. What is the value of RB that you got? 165.34 kilonewton is the value that you have got. So once you have got this, then you can find the reaction force in the other side. So you can say the sum of the forces are equal to 0. That means the forces acting upwards are equal to the forces acting downwards. With this idea, let us see what are the forces acting downwards. So the UDL which is actually, let me write this, forces acting downwards first and the forces acting upwards later. That will be easy for me as per this rule. Forces acting downwards is actually 30 kilonewton per meter, which is actually spread over what length? This is actually spread over 8.5 meters of length. So that is the load which is actually acting downwards. And there is one more load which is actually acting downwards. So that is 100 kilonewton is acting downwards. So that should be equal to the forces which are acting upwards. There are only two forces which are acting upwards. Those are the supports. So RA and RB. So RA plus RB. But you already know that RB value is this. So therefore, there is only one unknown in this equation. So you can find out the value of RA. So can you tell me the value of RA? The value of RA is 189.6. 189.6 kilonewton. So you're getting some odd numbers here because the numerical is actually given in this way. Once you have done this, then write these values on the diagram so that you don't have to every time look into this. So let us write this RA value. So this RA, like RA value as, which is equal to 189.6 kilonewton, and this RB value as 165.34. 165.34. So it is better you make this as last numbers as same. If it is 34, this can be 66 or something. Then it will add up. Then it will become exact values. Kilonewton. So kilonewton. Okay. Now once you have done this, let us draw SFD, shear force diagram. So we know the convention here. The convention is in any beam, if it is the reference section and anything downwards on the right hand side is positive. So with this idea, we start drawing the SFD. So let me draw a zero line here. Let me draw a zero line here for SFD. Okay, now there's 100 kilonewton going downwards. Okay, now let us assume that this beam is actually spread towards the right side of this 100 kilonewton. But even if it is actually quite lengthy on this side, since there are no forces on this side, the shear force on this part of the beam is 0. So let me, if I am on the right hand side of this 100 kilonewton, that there is no shear forces. So I write this as 0 kilonewton shear force. Once I move to the left side of this 100 kilonewton, suddenly from 0 it jumps to 100 kilonewton of shear force on the right hand side, which is downwards is positive. So therefore this goes up. So this is where I am marking as 100 kilonewton. And as I move the section here, you only see this 100 kilonewton, no other force. It will remain the same. So I will draw this 100 kilonewton as it is until it actually meets one more force here. Now if I jump across this B, then there is 100 kilonewton plus which is coming down minus 165 which is going up. As per this, the forces on the right hand side going up is negative. So therefore 100 minus 165, what will be the value? It will be 65.34 kilonewton. So when I take the section here, minus 165 plus 100, the value is minus 65.34. It will remain the same value throughout. So I will actually write this as it is. So this will remain 65.34 kilonewton. And then you can see from this side, if you see here, there is more and more UDL added, and that will actually try to increase this value. We don't know how it actually increases, and we don't have to worry about any points in between. So let us move to the next point here, which is this. So when I'm here, so I can take all the sum of the forces on the right hand side, or I can see what are the forces on the left hand side. Both I can do. So both will be correct. And since you are doing on the right hand side, let us continue doing this. Okay, now here it was minus 65.34 and plus there is addition of 30 into 5.5. So 30 into 5.5 is how much, man? 30 into 5.5. 165. So it is actually, so 165 plus minus 65. What is the answer? 100. So this will actually go from minus 65 to plus 100. So almost in the same line of 100 here, like this. So let me draw a line like this. Okay, this is actually 100 kilonewton as per this. 30 into 5.5 is 165. So it goes from minus 65 plus 165, it goes to plus 100 kilonewton. And then as we go here, it will try to reduce. So instead of seeing on the right hand side, let us see what will happen onto the left hand side of this. So here we have actually seen up to this point where we have not considered this force. Okay, we are here, we have considered only this side, but we have not considered this force here, which is actually 189. Okay, now we are seeing onto the right side of the section all this time. Let us see from the extreme end here. So is it visible in the video? Okay, let us see if this beam extended like this, if I actually see any force on this side, there are no forces. Shear force at this point will be 0. 0 kilonewton. Okay, and then now as I actually move like this, you know that anything onto the right side downwards is positive, anything onto the left side upwards is positive. So here this force which is actually acting downwards on the left hand side will be negative because upwards is positive. So here let us actually look at this point, it is 0. If I actually start moving, I get more and more UDL added here, and the intensity is for every meter it is 30 kilonewton for every meter. If I move by 3 meters, it is 30 into 3, which is 90 kilonewton, which is added, which is actually acting up downwards. So it is negative. So it starts going from 0 to negative direction. 0 to negative direction. So let me draw a line going from 0 to 90. So if this is 65, 90 has to be slightly more than that. So I will draw a line like this. I will draw a line somewhere here like this. This is 90 kilonewton. Okay, now this is 90 kilonewton up to this point. Now if I jump across this point A, then there is 189.66, which is almost equal to 190. So therefore, this which is actually acting downwards, UDL which is acting downwards, that is minus 90, and this reaction force RA which is plus 189. So minus 90 plus 189 will be equal to 100. So because of this RA, it jumps from minus 90 to plus 100. So these numbers are like not whole numbers, but here you got it like this. Okay, you can almost approximate it like this. So this is how you draw shear force diagram. Once you have drawn this, you try to shade this so that you understand what is above the zero line and below the zero line. Because since you are making this in a ruled book, whether the zero line is here or whether the zero line is here, it will be confusing. So all the area above the zero line, you please shade it like this. So people understand that this is the zero line, and again shade this like this, so you understand that this is the area below the zero line. So you see the variation of the shear force throughout. And you will see that this is the portion where you got the highest shear force, which is 100 kilonewton. Here it is 90. So there are a good number of chances that the beam may fail here, which is now it has got the highest shear force. If it is failing by shear force, the first chance of failure is at 100, which is the highest value here. throughout this point, at this point, the next chance of failure is at 90 and the next chance of failure could be at 65. Suppose if this beam is going to fail by shear, then the highest chance would be here and at this point. So we are done with the shear force diagram now. Now let us draw the bending moment diagram now. So let us first draw the zero line for the bending moment diagram. What do you think? This will have sagging or hogging? It will have both sagging and hogging. So the center part will sag, these sides will hog. So you have to have some space above the zero line. So this is the zero line that I am drawing. Let me draw the zero line a little bit below. Okay. So this is BMD. Okay, as per the convention, in a beam, it is a force which is trying to sag the beam, or a moment which is trying to sag the beam on either sides, which is upwards, that is positive. And the forces which will actually try to hog the beam is negative. So let us start with this convention from the right side extreme end. So here I will start. Are there any forces on the right side? No forces. So I write this as 0. Let me use a different color so that it doesn't confuse. 0 kilonewton meter. So here I was writing kilonewton. Here it is force into distance, so it is kilonewton meter. When I move to the left hand side of the beam, there is force but there is no distance. So force into no distance is 0. So when you move across E, there is no change. But when you actually start moving like this, with the distance, force into distance increases. So moment will increase up to this point. So about this point B, the moment value will be force into this distance. Okay, 100 kilonewton into 4. 100 kilonewton meter into 4 will be equal to 400 kilonewton meter. Will this be positive or negative? Any force which is acting downwards, this part of the beam will try to hog, so it is negative. So therefore, it goes from 0 to minus 400, which could be seen somewhat like this. So this is minus 400 kilonewton meter. Okay, and then as you actually go to the left hand side of B, there is no change. Right side to left side with no distance. It doesn't change because it is not shear force. And then you go to this point. When you go to this point, let me write it here. So bending moment at D. Moment at D is equal to this reaction force at B, which is actually 165.34. Guys, this force as per this, is it positive or negative? It's positive. So it's positive plus 165.34 multiplied by what distance it is? 5.5 into 5.5 meters. This is kilonewton. This is plus. And then this force 100 kilonewton acting downwards, that is negative. So minus 100 kilonewton. At what distance is this point? 5.5 plus 4, which is 9.5. It is 9.5 meters. So what is the value, guys?
Minus 40.
Minus
45.
minus 45.6, huh? 40.63 kilonewton meter. So this goes from minus 400 to minus 40. So minus 40 could be somewhere here. 0.63 kilonewton meter. It goes from this to this. And then, guys, am I right? So I was supposed to write here at this point. It is minus 40 here, sorry, not here. So here it goes from, not here, here, minus 40.6 kilonewton meter. Okay, and then let us now start seeing from the right hand side, because you have done it up to here. If you want to see like this, then there will be a lot of forces, UDL and all that. It may confuse you. Let us start from seeing from the left hand side of this beam. Okay, left hand side of the beam. Let us start from here. Any forces on the left hand side? No forces. So no force, no distance. So it is 0 kilonewton meter. 0 kilonewton meter. And when I am at A, so the moment at A, when I am at A, so UDL intensity is 30 multiplied by 3. I know anything going upwards like this, either on left side or right side, is both positive. So this UDL which is acting downwards on the left hand side of this point is negative. So 30 into 3, which is 90, minus 90. So 30 into 3, so intensity is 30, distance is 3 meters, it's spread over 3 meters. So it goes from 0 to minus 90. If this is 400, then 90 should be approximately equal to this. So let me draw this line here like this. Guys, we have made that. Now we need to be careful here. Whenever there is an horizontal line or a constant line, below you will have an inclined line. Whenever you have got an inclined line here, you will have a parabola here. Because with respect to distance, not just the distance is increasing, load is also increasing. Distance is increasing, load is also increasing. So therefore, it forms a parabolic path. So it should be a curve like this. It should not be a line. So you can actually draw like this or like this. It doesn't matter. But the examiner observes that it's not a line. Okay, never draw a line. Okay, so you can even draw like this. If you want, you can even draw like this. Okay, it doesn't matter. But it should not be a line. So this goes from 0 to 90 kilonewton meter. And then at D, it is 40.6. So how does it actually vary? Should I actually draw it with some curve, or will it actually go like this and come back is a big question. So we'll have to do some circus for this. Guys, basically, whatever the answer that you are getting is the area of this, which is actually 3 into, so half into base into height, half into base into height. So that is half into base and half into 3, that is 1.5. 1.5 into 90, that is actually 135, which means we have gone wrong here. So that means this is the answer that we have got is wrong, because while calculating the moment at this point, we said there is UDL on the left hand side, 30 into 3, which is 90. So this whole UDL has to be placed at the center for consideration. 30 into 3 is 90. 90 into 1.5 is 135. So this is not 90. This should be 135. So suppose this is 400. 135 could be somewhere here. So you can draw somewhere here 135. So this is 135. So in the examination, you can use this method of adding the area. That will help you to confirm what you have made is right or wrong. You can also confirm here also. Guys, here some people do this way. Here they only look for this area. Here there is no area on the right hand side. If you see here, there is area getting added. So what is the height here? Basically 100 kilonewton. 100 into 4 which becomes 400. So that is getting, so as per this is minus, it comes exactly ulta. And then this is in the opposite direction. So as it is in the opposite direction, as you actually go here, it starts getting deducted. I mean, it starts getting like this. So 400 minus this 65 into 65.34 into 5.5. That will give you this value like this. So you can actually look at this area. If you integrate this shear force, we always say the relationship between bending moment and shear force is that bending moment is the integral of shear force. Integral and sum. Integral of shear force. So therefore we do that way. So you can confirm whatever the answer that you got by actually looking at the area of the shear force and adding the area from right to left like this. Okay, you can use the convention. As per the convention, you can add and deduct. Now you should get the same answer. Here also, when we actually checked the area, we got the different answer. So we felt whatever the answer that we have earlier made is wrong. Okay. Once you have done that, so up to here, the shear force was below and the bending moment was below. Now, since we are having an area above, definitely, which means that it starts going to rise like this. And it will start going to rise up to this point, then again it starts getting deducted. So which means that at some point here, it will be the maximum, and then again it starts getting deducted. So this will be the point wherever shear force is 0, that point will give you the maximum bending moment. The maximum bending moment could be like this, and it can reach a value like this, and again it can decrease. What is the value here at this point that you have to find out? So if you want to know the value at this point, first you should know what is this location of this point. Where is the shear force equal to 0? So can you use, now what do you use? What principle do you use? Similar triangles principle. Similar triangles principle you use here. So here the total height of this is 100 plus 65. 100 is here, 65 is here. So for 165 height, the base is how much? 5.5. So for 165.34 height, the base is 5.5 meters. And for 100 mm height, what is the base? For 100 mm, so for this side, what is this? So this is ratios and proportions. So if you want x, you should multiply, now you should cross multiply. So x is equal to, in the ratio of 5.5, it is the ratio of 100 divided by 165.34 multiplied by 5.5. Can you tell me what is this value? 3.326. So you get this value of x as 3.326 to be precise meters. So shear force becomes 0 at a distance of 3.326 meters, and at this location the bending moment will peak and again decrease. So I want to know what is the value of bending moment at this point. So what I do is I go to this point here and start checking what is the bending moment at this point. So this distance is 3.36. So I want the bending moment at this point. You can look at the bending moment on the right hand side. If you look at the bending moment, here you will have UDL. Here there is one force. Here there is one force. UDL, one force, two force. If you look on the left hand side, we will have one stretch UDL and one force. So looking to the left side is easy. So what I will do is I will look to the left side and find out the bending moment. So here bending moment at this point, let me call this section as XX. Which is at a distance of 3.326. Look to the left side here. Then Here, the UDL which is acting downwards, is it positive as per the convention or negative? It's negative. So, bending moment at xx is equal to UDL intensity minus 30 into this whole length of UDL. What is the length here, guys? Can you tell me? 3 plus 3.6. Total like ಎಷ್ಟು? 6.36. 6.36 is the value which is negative. Which is negative because it is acting downwards. This is negative. And this UDL has to be placed at the center of the UDL. ಇಷ್ಟು UDL ನ ಸೆಂಟರ್ಗೆ ಹಾಕಬೇಕು. ಸೆಂಟರ್ಗೆ ಹಾಕಬೇಕು ಅಂದ್ರೆ ಇಲ್ಲಿ, so that is 6.36 divided by 2. Okay. And then there is one UDL, sorry, there is one force which is acting upwards, which is RA. So that is 189.66, which is positive. So that becomes 189.66 at a distance of 3.36. Can you tell me what is the answer here? Huh? 5? Now, if I actually calculate this, I get the answer as, is it minus 30.51? Plus 35. Plus 30.5. It's plus 30.51. So which means that this is not going downwards, it is going upwards. So that means the direction that I have guessed is wrong. This is going to be plus 30.91, and I could have actually predicted here. Here, this was actually in the negative. That means with this addition, it went to minus 400 here. And since it is on the other side, it started increasing like this, and it went to minus 40.6. Then you will see that there is also plus here. So it should go like this. It should go like this. So I should have actually predicted that looking at this, since it is not changing the direction above the zero line, some more area should get added here. It will actually keep going in the same direction. It actually did not go from plus to minus here. So therefore, this is minus. It was 0 here. As you went like this, it went from 0 to 400. Then it is on the other side. It started decreasing here. It started decreasing here. Again, there is some more area getting added here. So you will see like this. So this is like this. And once it actually changes direction here, then it is on the other side. It again becomes minus. Then it starts going like this. So you will see that this is how the bending moment diagram has to be written for this. So the final bending moment diagram for this diagram is 0, minus 135 kilonewton meter, 30.91 kilonewton meter, 40.6 kilonewton meter. This is 400 kilonewton meter, and this is 0 kilonewton meter. So once you have done this, then you can actually shade this. You can shade this diagram here this way. Now, you know what is contraflexure, no?
Yes.
Can you contraflexure?
Sir, opposite flexing.
Opposite flexing. Bending moment, if it is going from minus to plus, it is contraflex. It is actually changing direction of bending. So ಈ ತರ ಇದ್ರೆ ಇದು ಹಾಗಿಂಗ್, ಇಲ್ಲಿಂದ ಇಲ್ಲಿವರೆಗೂ ಹಾಗಾಗ್ತಾ ಇದೆ, ಇಲ್ಲಿಂದ ಇಲ್ಲಿವರೆಗೂ ಹಾಗಾಗ್ತಾ ಇದೆ ಬೀಮು. So you can see the beam, because of this load, it will actually keep going like this, and here somewhere it will start to sag. It will start to sag here, somewhere like this, somewhere like this. So the point where it will start to change direction is one point of contraflexure here. So there is one contraflexure here. That means bending moment is changing from minus to plus. Then there is again one more contraflexure here, because again the bending moment is changing from plus to minus. So that means here also the beam will bend like this, from hogging to sagging, and again this beam will bend. So you will see that, so the beam would actually bend like this. So that means here you got hogging, and then again here you got sagging. Where this hogging changes to sagging, so that is one point of contraflexure which is referring to this point. Again this sagging plus this hogging, at this point it will change directions. So that is again one more contraflexure. So you don't have to find contraflexure unless it is asked in the numerical. Because finding this again will lead to a quadratic equation, solving of a quadratic problem. So with this, the problem is finished because we have drawn SFD and BMD as it was asked.